Hi everyone, we are back and we are going to go through our problem set 7 solution videos. So we have the following ceramic material under the stress state. This should look familiar. It was in our problem set previously. So let's go ahead. We're going to solve for that stress tensor again. You can solve for it again, or you can just basically look at the values from the last video for look at the stress and strain tensor. So ceramic, 0.2. The strain in the 3 direction is actually 30 times 10 to the minus 2. And you can look at our problem set 5 solution video to double check this. Divided by 30 times 10 to the minus 2. Good. So there will be a strain in the 1, 1. We know that open the attached, so we know E22 is equal to 0. And then there should be a stress. There's going to be strain in all those other directions except for that. So our delta T is 0 for this problem. And let's go ahead. E11 we don't know. E33 we do know. Sig11, Sig22. Oh, actually, so there we do know what excuse me. Sig 11 will be equal to 90 times 10 to the 3 divided by 35 times 10 to the minus 2 squared. We'll cover that, cover this, and that's just from what we had previously. So we'll go ahead and then we will solve for all those values. Excellent. So, and we know Sig22 and Sig33, good. So let's go ahead and let's define those and we'll be able to work through the rest of this problem. Sig33 here. So we know that our Sig11 is positive. So Sig1, our largest normal stress, we're in the principal stress state. So this is going to be Sig11. Our Sig2, because let's ask the question, is Sig22 greater than Sig33? True, so Sig2 will be equal to Sig22 in this particular problem, just because we're ranking, remember, Sig1 is the largest, Sig3 is the smallest, Sig33. So now we can do, for our ranking criteria, what is our, so we are working the black material. So the black material, the screen is having a little bit of issue catching up. Black material, I would say our yield stress is probably around, let's say like 70 megapascals, looking at that curve. So sig y is equal to 70 times 10 to the 6. So is sig 1 greater than sig y? Nope, so it won't yield. Is sig 1 minus sig 3 greater than sig y? Yes, so it will yield there. And then finally, for the von Mises criteria, it's going to be is 1/2, or actually, excuse me, square root of 1/2 times sig 1 minus sig 2 squared plus sig 2 minus sig 2 minus sig 3 squared plus sig 3 minus sig 1 sig 3 minus sig 1 squared. And then is this greater than sig y? Yes, so it will not yield via ranking, but it will yield via Tresca and von Mises criteria, respectively. And I think that was what the problem was asking for. Let's scroll up. Good, we've got that. So this is a ceramic material. So if I have a crack size with this and a strain energy release rate, will it fracture? We can't answer that question. Because again, we could only use, for a ceramic material, we have to use this, square root 2 gamma Griffith criteria over pi a, or our fracture toughness equation, which is F, which we set this basically equal to 1, stress square root of pi a. So we can solve it for those other systems. And when we're looking for cracks, we're only looking for, again, tension values, so for fracture. For a fracture, or for basically materials that fail under compression, typically you may think about buckling instabilities if you're dealing with kind of beams and those things like that. You can also crack, in compression too, but our equations weren't developed in such a way. So we're going to ask basically crack size of this and a surface tension, will it fracture? So we need to solve for sig F equals square root of 2 times, we're given that surface tension, which is 378, times our Young's modulus. We should just do this all here. 2 times 378 times 378 times our Young's modulus here, divided by pi times our crack size is 87. So 87 times 10 to the minus 6. So let's solve this numerically. We see that's our value here. Our value that's applied is such. So this is the stress required to fracture it. So the stress is not larger than this. So nope, it will not fracture. Then what if it's the other situation? So now we can solve 47 times 10 to the 6. That's our fracture toughness, set equal to sig at failure times square root of pi times, now it's 147 times 10 to the minus 6. Let's look at that numerically. Numerically here. And again, I don't think we're going to fracture looking at the values that we have. Nope. Okay, so no crack, and that's it. No cracking today. All right. So, and I actually happen to remember this solution. Let's go ahead and clear the kernel. Quit the kernel. And actually, we don't even need to really care too much about this. And even our previous solution. Let's go ahead. So we're looking about, again, this pipe material we solved in the last problem that was a metal. So if it's a metal, we know we can use either this equation or this equation. So we're also told that our radius, where's our R? Actually, I still have this saved from the previous notebook. Here's our radius, here's our thickness, here's our del P. So here's our sig H. So our sig H is what we're going to use to solve this problem. So I'm going to say, what's the crack size that will lead to fracture? So I'm going to solve that 22 times 10 to the 6, set it equal to sig H times square root of pi times A, and that will be your crack size. So we could use either equation here, but for metal we can't use the Griffith criteria. So we can't use this for Griffith, for a metal or a polymer. All right, let's look at some of these deformation mechanism maps. Fill out the regions. I'm just going to do it for one. Again, theoretical shear, DG, dislocation glide, elastic. This is going to be power law creep. This is going to be Navarro-Herring. This is going to be Coble creep. And you can do the same for the rest of the curves as well. Let's see. Draw the stress strain curves for A, B, C, and D. So I'm going to call this A, B, C, D. So if I'm looking at a stress strain curve here, the thing that we're seeing that's changing is our yield strength. Our yield strength is increasing and the Coble creep region is increasing, so stress and strain. So these were either work hardened or grain size strengthened. So I'm going to say that this is going to be, actually I should erase a little bit. I didn't want to erase all of it, but. So I'm going to call this is going to be my D. Then same slope, but lower yield strength, higher strain at failure. This is going to be my C. This will be my A, and then this will be my B. There we go. What are strengthening mechanisms? It's going to be either work hardening, so scales as dislocation density to the 1/2 power, or grain size strengthening, which scales as dg to the -1. Excellent. Why does it dominate at higher temperatures? So remember, it is true for Nabara herring that basically we're looking at diffusion in the lattice, which correlates to Nabara herring, is always less than diffusion in the grain boundary because the activation energy to move in the lattice is greater than that for the grain boundary. Now, it is true that atoms are always moving faster along or in the grain boundary, but eventually, as temperatures increase dramatically, these little atoms will move and like basically the collective motion of this, like 99%, will beat out the atoms essentially in this grain boundary. Yeah. And you can kind of get more in detail, and I expect you to do more in detail with some of the equations in that, the strain rate for those problems as well. Excellent. Let's look at our stress curves here and focus on 3 materials. So black, the dark blue here, and then the cyan. Draw the deformation mechanisms for these 3 stress strain curves. So what you're going to be looking at here, what's changing, you have your, this is stress over G, and this is T divided by Tm. This doesn't change. This would be basically, your dg for the black. Then this would be the dg for the blue, dark blue, and then this would be your dg for the cyan. So your yield strength is decreasing, as we can clearly see here. These are also 3 different materials. So basically, the Coble creep region will not change because the mechanisms here are going to be the change in yield strength is correlated to the concentration of solute to the 1/2 power, or they're going to be basically precipitate hardened. Or precipitate strengthened. I shouldn't say hardened, excuse me. Precipitate strengthened. So those are the mechanisms that will occur here. So boom, boom. What happens to critical radii if the volume fraction increases? What are the energy contributions? Excellent. So if I have a system like this, system 1, system 2, and system 3. System 3 has the largest volume fraction, so I have lots of particles in here. Here I have kind of medium, and then here's just 1. When a dislocation line goes to a particle, I could either basically cut that particle in half, and in doing so, I create surface area. Or I can approach this little precipitate, and basically I can loop around, and then I keep moving in terms of my dislocation line here. So those are kind of the energy contributions, and that's, to bow around it, I have to deal with curvature. So I want to cut small particles because this increases, I'm basically increasing the area, my surface area, and that's going to scale as like r squared. And this, I want to bow around particles that are very large. So I want to bow large, I want to cut small. When I'm looking at how this can change, basically based on the radius of my particle, if I'm looking at 2, there's going to be a certain particle size, some critical particle size, RC, where there's a maximum particle size that's the most difficult to get around, and I'm going to cut, again, small particles, I'm going to bow around these particles. Now, if this is system 2, system 3 is going to have a larger, basically, peak here. But if I go and I move through, like it's going to be harder to cut particles because there's so many particles, I'm creating much more surface area. So the curve for number 3 is going to look like this. My basically peak yield strength has increased because there's more particles that I have to navigate through, which makes sense. And I want to cut less particles because I'm cutting from here to here. Here, I'm only cutting from here to here. I'm bowing around the rest. Now, comparing 2 to 1, now it's even easier, and I don't mind cutting particles necessarily here. So this would look like my curve for number 1. And that's it. That's your problem set 7. So we'll see you in the next video. Thanks. Bye.